Okay, so David Yost, our last speaker for this session, and David will talk about diametrally maximal sets. Please, David.
Okay, thank you, Nadia, and thank you for the invitation to talk. I've always got a problem knowing what to talk about, and I got some motivation a few weeks ago when Wilfredo Sosa gave a talk in the Macau seminar series. So there's the list of webinars, the archive there. And I have to say, I haven't got a very elegant presentation today. It's a bit disorganized, but I'll begin with Wilfredo's slide, the relevant one. And what interested me was proposition 12. If you've got a mapping which satisfies all the assumptions of the previous proposition, and I'm not going to worry about what those assumptions are at the moment, it's maximal pre-monotone if and only if C of X is a diametrally maximal set. So I thought, oh, people in optimization are interested in diametrally maximal sets, so maybe this will be a good topic to talk about. And I haven't worked out what the rest of Wilfredo's proposition means. I'll come back to that one day. So what is a diametrally maximal set? While it's diametrally maximal or diametrally complete, I'll hop back and forth between these two terms. In a metric space X, but mostly I'll be working in a norm space, and you can think of that as Rn for the most part. It's diametrally complete if whenever you add a single point to the set, the diameter strictly increases. Or in other words, you can't add any more points to the set without increasing the diameter. And this is an old definition, goes back to Meissner in 1911. Now, a diametrally maximal set has to be bounded and closed and convex. So for the most part, these are the only sets that I'll consider. Everything is going to be non-empty, closed, bounded, and convex. And you can always form the completion of a set. There is always a maximal set which is diametrally complete, which contains any given bounded set, and that's an application of Zorn's lemma. You consider all the possible diametrally complete sets that are contained in a given set, and they certainly exist because every ball is diametrally complete. And you order it in the natural way, and Zorn's lemma gives you a maximal element. So they exist. So I'll call a set constant width if, this is not the simplest definition, but I've got the simplest definition on a coming slide. A set is constant width if it's got the same width in every direction. So one way to define that is in terms of supporting functional. So X is now a norm space, and for every supporting functional, or well, actually for every norm one functional, the difference between the supremum and the infimum of the functional on that set is a constant. And you call that the width of the set. An equivalent way of saying that is that if the difference set is a ball of radius lambda. Now, it's an easy application of the separation theorem that every set of constant width is diametrally complete. And it's an interesting question whether the converse is true. And in the Euclidean spaces, they always are. Okay, here's the definition I really wanted. Set is constant width. This is equivalent to what was on the previous slide. If the difference set, the set of all x minus y, such that x is in C and y is in C, if this difference set is always a ball. And the next definition, a set is constant radius. I may not talk much about this. The radius, which I've defined later, is the radius of the smallest ball centered at X, which contains the set C. And if this radius is equal to the diameter for every point on the boundary, we call the set a constant radius from the boundary. Now, what are some examples? Well, here is an example of a set of constant width, which is not a ball. So obviously every ball in every norm space has constant width. Here is an example which is not. This is a rouleau heptagon. So the boundaries of this coin are arcs of circles. And because it's a constant width, it can go into a slot machine and touch both sides, and the machine will know that it's a coin of the correct value. So there's a practical application. Here are some more examples, some coins, but one of our favorite pictures, a Venn diagram of three intersecting sets, actually gives us a curve of constant width. The shaded region in the middle is the so-called rouleau triangle. So no matter what point I choose on the boundary, if I take a supporting hyperplane in this direction and a supporting hyperplane on the other side, the distance between the supporting hyperplanes is always the same. And there's an example which shows that the rouleau triangle, no matter how you turn it inside two supporting hyperplanes, it would always touch both sides. Now, I could talk about more general norm spaces, but let me just introduce the notion of reducibility. We call a set reducible, a convex set, which has to be symmetric, if we can write it as the difference set of two other sets. So in this case, what this diagram shows is that the regular hexagon is the difference set of the triangle. So if I take the triangle, doesn't matter where I put the triangle, give names to the vertices, and calculate all the possible differences, what I get is going to be a regular hexagon. So this is possible actually for any two-dimensional symmetric body, is reducible except a rectangle. A rectangle is, or a parallelogram, is not reducible because it can only be decomposed as the difference set of another parallelogram. But everything which is not a parallelogram is reducible. And this has been known for a long time. Euler noted that the Euclidean disk is the difference set of the rouleau triangle. So the same picture, if I change the triangle to a rouleau triangle, the hexagon turns into, well, the rouleau hexagon is just a disk. And the same is true in higher dimensions, in 3 dimensions, in Rn in general, or Rd. The unit ball of Euclidean Rd is always reducible. Now, this is not always true if we take different norms. So here is, I think, the simplest example. This is my own. So if we take a 3-dimensional space with this norm, so what we're doing is we have the L1 norm here, the octahedron, and then we cut off the corners of the octahedron. So this is a truncated octahedron. What you get is a polyhedron, which is simple. Every vertex has degree 3. And every facet, in fact, is going to be a square or a hexagon. And because the facets are all small, two opposite facets never give you the whole polytope, it follows that unit ball is this unit ball for this norm is reducible, or in other words, the truncated octahedron is reducible. On the other hand, if I take a short calculation, I'll let S be this set, the convex hull of these 4 points. So EI, E1, E2, 3 are the standard unit vectors. With respect to this norm, this set has diameter 2. But now, if I take the intersection of the balls with center at these points and radius 2, I get exactly this set. I don't get any more points, I don't get any less. And that shows that this set is diametrally maximal. But if I calculate the difference set, it's not a ball. It's a proper subset of the unit ball because it doesn't contain this point. So in general, a diametrally maximal set does not have to be a constant width. Now, this was known much earlier, so I have a few more definitions first. So this is a definition I omitted before. The Chebyshev radius of a set about a point X is the furthest away that you can get from X in the set. The Chebyshev radius of a set A with respect to a set of B is the smallest possible Chebyshev radius for the set A with respect to points which belong to the second set B. Now, Eggleston was the first to show that a diametrally maximal set doesn't have to be a constant width. And he gave an example of a three-dimensional norm space with a smooth, strictly convex norm where this happens. And sometime later, I showed this is actually a very common phenomenon. So if you have, take any vector space, Rd, for any value of d bigger than 3, and consider all the possible norms on it. The set of all possible norms has a natural metric, the Hausdorff metric. And with respect to most norms, most in the sense of bare category, your norm space will be smooth and strictly convex and contain diametrally complete sets which are not of constant width. And the reason for this is with respect to most norms, the unit ball is smooth, strictly convex, and irreducible. I'm not going to go into the details of why that's true. It's a bare category argument. And if you're used to bare category, it's not difficult. If I consider any such norm, I claim that any such norm has this property. So I have to find a diametrally maximal set which is not of constant width. Well, with these other conditions, it's not hard. If I take 2 points in the unit sphere which are at distance 1 apart or closer, then the intersection of the ball centers 0.5 and the ball center x radius 0.5 is exactly the point 0.5x because the norm is strictly convex, and the same happens for y. So if I take any complete set of diameter 1 which contains these 3 points, then that set cannot be contained in any ball of radius 0.5. And so that set cannot have constant width. But it can be diametrally maximal. So there's a big difference between these two. So, okay, I've got things out of order. So I've gone back to my definition of radius here. So the Chebyshev radius of a set is the smallest radius that it can have with respect to a point anywhere in the space that you're sitting inside. The Chebyshev self-radius is the smallest radius the set can have with respect to centers which are in the set or the convex hull of the set. And this can be strictly larger than the absolute Chebyshev radius. And we call a set diametral if its self-radius is equal to its diameter. Now, how far, I want to ask the question, how far a constant width or diametrally complete set can be from being a ball? And I have here another example of why it matters to know this. So the Challenger Space Shuttle incident was caused by failure of O-rings, and before the launch, people had checked that the O-rings were really O-shaped and circular, And the way they checked that was to measure the diameters at 6 different positions, 30 degrees apart. And okay, that tells you that the set may be of constant width, but sets of constant width are not necessarily circular because the diameters might not intersect at the same point. So sometimes it's important to know that a set of constant width does not have to be a ball. Now I'm going to talk a bit about infinite dimensional norm spaces. A constant width set can have empty interior. This is not true in finite dimensions. And the simplest example, it's not a hard calculation. We take the Banach space C0 and we look at the positive elements in the unit ball. So all the sequences which converge to 0 and which only take values between 0 and 1. This set has constant width, but it's not a ball. It doesn't have a center. The point that you expect to be the center is not in the space because there's no sequence that converges to 0 that could be the center. And in fact, this set has empty interior. In reflexive spaces, it's been an open problem for a while, finding a constant width set with empty interior, but we have some examples. I'll discuss them shortly. In a finite dimensional space, this doesn't happen. A set of constant widths must be full dimension. You take its affine hull, you must get the whole space. And if that's true, then it must have empty interior. So you expect constant width sets to be plump in some sense, and more precisely, if W is the width of the set, then a constant width set must contain a ball of radius W divided by the dimension plus 1. This has been known for a while, so you're guaranteed interior points, but the size of the interior goes down with dimension. Klee's proof is a bit challenging, and I've often wondered if it's possible to deduce this result just from Helly's theorem, but I haven't succeeded. And there's an example here which shows that this is the best possible. You take RD with a slightly unusual norm, sum of the elements plus the sum of the absolute value of the elements plus the absolute value of the sum of the elements, and you take the convex hull of the unit vectors in the origin. So this is a set of constant widths which contains a ball of exactly this radius, 1 over d plus 1, and nothing larger. So as I've said, this is not true in infinite dimensions. C0 gives you a natural example. The same is true in L1. In fact, L1 does not contain any sets of constant width which are not balls. More generally, if you've got a Banach space with a property that it has a face in its unit ball, and the convex hull of this face and the opposite face give you the entire unit ball, then the dual space contains no non-trivial set of constant width. In the dual, every set of constant width has to be a ball. And as I said before, in reflexive spaces, it's an open question. And this is joint work with Elisabetta Maluta when she visited Ballarat 3 years ago. We can renorm many particular Banach spaces to have examples, and it's not hard. So every Banach space which admits a good basis can be renormed to have a constant width set with empty interior. And I'll just skim through the proof. So you have a basis. The basis gives you an induced positive cone, and you take the intersection of this cone with the unit ball. So this is exactly what happens in C0. The intersection of the unit ball with the positive cone induced by the basic sequence. And because the sequence of coefficients for any element converges to 0, the interior is empty. And the unconditionality of the basis, you have to check what unconditional means and do some calculations. S minus S must contain a non-empty ball. So S minus S is closed, but it must have non-empty interior. So you just, this set has non-empty interior, this is closed, and the result says there is renorming. You simply take this set, S minus S, closure if you need to be the unit ball for a new norm. And then you've got a set with non-empty interior with respect to this norm. Okay. Sets of constant radius. Any set which is diametrally complete has constant radius from the boundary. So we have this relationship. Every set of constant width is diametrally complete, and every diametrally complete set has constant radius. And we'd like to know about the converse. So are these two classes equal? Can these inclusions be reversed? Oops. Well, here are some partial results. Every set of constant width is diametrally complete. This is true in a Hilbert space, or it's true in Euclidean Rn. It's also true in every two-dimensional space. So the minimal counterexample to this has to be three-dimensional. It's also true in C0. And that's not trivial. It's also true in a space of continuous functions if the domain space is extremely disconnected, because in this case, diametrally complete sets have to be balls. This is a generalization of the fact that in a two-dimensional space, the parallelogram is irreducible. And as we've seen, it's not true in three-dimensional spaces. In a finite dimensional space, diametrally complete and constant radius from the boundary are equivalent properties. In infinite dimensions, this is not true. In the sequence space L infinity, counterexamples are known. So if a set has constant radius, its interior is empty if and only if it's a diametral set. So this is a new relationship. So the question of whether the set has empty interior and whether the set is diametral, these are equivalent for sets of constant radius from the boundary. For a diametrally complete set, emptiness of the interior is equivalent to being a maximal discrete set, diametral set. Oops. And I know it's, as the last speaker of the morning, I'm not supposed to hold people up from their lunch, so I'll stop on time.
Okay, thank you very much, David. So we have time for questions.
Hello, good evening. I have enjoyed very much this very nice talk. Thank you, David. And I have a question. If I understand it correctly, I mean, in finite dimensions, I mean, you gave an example of a norm in which there are diametrically complete sets which have not constant width.
Yes.
Okay. But this is true in the case of the Euclidean norm.
Yes.
In every dimension.
Yes.
Can you give some geometric intuition why the Euclidean norm is so special, or which other norms in finite dimensions have the same property? What makes the Euclidean norm so special?
Well, the Euclidean norm is special in so many ways. It's so long since I've actually looked at the proof of this, it's hard for me to answer. But you know, there is a book by Diametrally about characterizations of Hilbert spaces, characterizations of Euclidean norms. There are hundreds of conditions which are equivalent to a norm being Euclidean. Yeah, so the Euclidean norm is just the best in so many ways.
Yeah, but my question was, what's the crucial property of the Euclidean norm that is relevant in this case? I mean, I mean, to give an example, may it be that every boundary point is an extreme point? May it be that it's invariant under orthogonal transformations? What's the crucial property that that makes this property possible?
Look, I have to say it's so long since I've looked at the proof that I don't remember. I'm afraid, but I can chase it up.
No. I mean, just,
yeah.
Because I think there is no easy proof, no easy proof of this.
No.
Of this. Mm-hmm. Okay. Thank you.
Okay, so more questions? Okay, so if no questions, then first of all, I would like to thank David